Hello, everyone. I'm very happy to introduce Professor Vivek Srikumar from University of Utah. He is an associate professor in the School of Computing, and at the same time, he's also currently a visiting researcher at AI2. So Vivek's research lies in the areas of natural language processing and machine learning, and has been primarily driven by the questions arising from the need to efficiently reason about textual data with limited supervision. So Vivek's research has been published at many AI, NLP, and machine learning venues, and has been recognized with the Best Paper Award at EMLP 2014, and honorable mentions from Cornell 2019 and the IEEE Micro Magazine. So his work has been supported by research grants from NSF, US, Israel, BSF, NIH, and awards from Google, Intel, NVIDIA, and Verisk. So he has also organized several workshops hosted at primary ML and NLP conferences around a theme of how learning and structured knowledge intersect. So furthermore, he has served as Associate Program Chair of AAAI 2022 and the Program Co-Chair of Cornell this year. So he was a postdoctoral scholar at Stanford University before moving to Utah, and prior to that, he obtained his PhD from UIUC with Dan Ross. So today, Vivek is going to talk about the topic of dissecting NLP models and mending them with logic.
Thank you so much. Let me share my screen and then we can get going. I hope you can see the right thing. Okay, cool. Awesome. Thanks so much, Muhal, for the introduction. Thanks also for inviting me. I'm very excited to be here and tell you about some recent work that my students and collaborators and I have been doing. And this is this work, as I said, there are many people involved, and I'll probably point to the key people in each different each piece as it comes along. I want to start off by kind of examining this alchemy that we call Bertology, where we want to take some input text and convert it into some output through these models that I'll collectively call BERT. It's just a stand-in for many different kinds of models, but really they kind of have a similar flavor. And in fact, not just do the models have a similar flavor, the recipe for using them is also kind of well defined. So you start off with pre-trained BERT, and I'll use the name BERT, as I said, for many different things. You collect some labeled data for some tasks that you care about, and you pour the data into the pre-trained BERT. This is the process of fine-tuning, and that gives you fine-tuned BERT that is now a specialist on this data set. And now we can take this fine-tuned model that can produce outputs over distributions and evaluate them. Actually, ideally, you can take these fine-tuned models and use them, but let's focus on the evaluation. What does evaluation mean? Typically, when we think evaluation, we ask, does this model that we've just fine-tuned or trained mimic people well? So we have metrics like accuracy or F-score and such things. And if you want to talk about models that produce text, we have various named metrics. Sometimes we can have metrics that are specialized to the task at hand, or maybe we just can call some people and ask them to tell us if the model is good. One way or another, all of these approaches for evaluation essentially look at whether the input text and the outputs that the model produce have some kind of affinity, whether they are correct for each other. And one of the questions that I've been thinking about for a few years now is, can we do more? Model evaluation should help us understand models better. Let me give you an example of an evaluation that goes beyond accuracy. And I'll use the task of natural language inference for this example. This task will be a running example through this talk. So you're given a premise, P. Here the premise is John is on a train to Berlin. And we have a hypothesis H, John's traveling to Berlin. And we are asked, does P entail H or contradict H, or are they unrelated? In this case, let's say the model predicts that the premise P entails the hypothesis H. which seems reasonable. Now, let's say we have another sentence, Z. And Z says John is having lunch in Berlin. And let's say the model predicts that H contradicts Z. And we could maybe justify this by saying John could not possibly be traveling to Berlin and currently having lunch in Berlin. So yeah, the model seems reasonable. Now, let's say the same model, when given P and Z, says there's no relationship between them. Now, if you look at the sentences and think about it a bit, you'll see that the same system could not possibly hold these three beliefs. It violates an invariant. If P entails H and H contradicts Z, then I don't need to even think about P and Z. I know that P should contradict Z. This is from the definition of these of the labels. And yet, a model that gets almost 90% accuracy on the official benchmark violates this rather simple invariant on nearly half of a large collection of examples. This exact invariant. So this means that the model is not doing something right, even though it looks like it's pretty good. It gets 90% accuracy. So this is what this is the style of evaluation I mean when I say evaluation beyond accuracy. We can actually take this argument a little further. We could ask, knowing that this invariant exists, can we use this theory, I'm putting theory in quotes here, to improve the model? So I'll touch upon both these questions later in the talk. So let's come back to this question of evaluation. Standard evaluation essentially takes a model and asks how good is a prediction for an input example. We could do other things. For example, we could introduce control changes to the inputs where we know what the output should be and ask, does the model react in a predictable way? We could do something else, like what we just saw with the entailment example or the textual NLI example. We could ask, is the model self-consistent in its predictions over related examples? Another kind of evaluation does not really look at the input and output, but we can peer into the model and ask what's happening inside this black box. We can open the black box. All of these kinds of evaluation are not just new ways to think about evaluation. I mean, yes, of course, I'm not the first person to say that these kinds of things should be done, but I'm going to talk about specific instances of this, and hopefully a bigger point emerges from that. But in addition to the evaluation story, I think we can also treat these kinds of evaluation as opportunities to think about how to train models, and we could kind of invent new ways to build models. So this is the story of the talk. I'm going to talk about dissecting NLP models, and I'm going to talk about fixing them. In the first, on the dissecting side, I'm going to talk about two different ways of looking at models, where I want to introduce this idea of tasks as contracts that we can use to kind of guide our evaluation. And we can alternatively look into the black box using tools from geometry. On the mending side, we can use this idea of contracts to define rules that can then guide model behavior. So let's go into this one at a time. So with respect to how tasks imply contracts, the starting point of this line of thinking is a set of questions that kind of have been bothering me for the last few years. Are we really making progress in NLP, or are we selectively exploring data sets, maybe inadvertently, where current models succeed? In fact, are our models fooling us into thinking that they are better than they actually are? I am starting to believe that the answer to all three questions is yes. But let's kind of dive into a formalization that can kind of help us explore these questions a bit. I'd like to present a particular mental model that I use for thinking about this. Tasks, at least tasks that require labeling examples, define predicates, not data sets, but tasks. For example, the natural language inference task defines three predicates called entail, contradict, and neutral. When we have an example that's like the one on the slide, with John being on a train to Berlin and traveling to Berlin, when we say that this entails the premise entails the hypothesis, we're really saying that there are three propositions: entail PH holds, contradict PH does not hold, and neutral PH does not hold. This is the these are the predicates that this task gives us. Labeled data sets are essentially examples of these predicates. And the goal of a model is to take such a labeled data set, and then when a new example comes along, try to find the best predicate given the arguments. Now, it may seem like I'm just rewriting what's already there, and in some sense, that's what it is. But I want to kind of highlight the distinction between tasks and data sets. A data set can be biased, either deliberately or not, because of the way it samples examples. And because our models are built on data sets, these biases can percolate into the models. But when we think about a task at the definitional level or as a specification, a task specification requires two kinds of contracts from the predicates it contains. Irrespective of what the training data contains, the user of a model, let's say, that produces these predicates would expect the task, the model to generalize to new kinds of examples and to satisfy certain kinds of task-specific properties. Both both of these things in orange here, the new kinds of examples and properties, are going to be task-specific. Let's dive into both of these points one at a time. What do I mean by generalizing to new types of examples? The standard protocol for empirical evaluation in this sort of a learning based world that we live in involves collecting, given the task definition, we collect a training set, we train a model, then we evaluate it on a test set. But typically, the test set is distributionally similar to the training set. This is where learning theory tells us we can get some success. Now, what I'm arguing is that in addition to the standard test set, we need to have multiple other test sets, each of which is constructed carefully in that it differs from the test set one along a particular aspect. And we'll see two examples of these, what I mean by that. But essentially, by evaluating models along these sort of predefined aspects, allow us, we will be able to understand model behavior and, importantly, model failures, so that we can, in some sense, decide when and where these models should be deployed. And perhaps the most important thing here is that this kind of multifaceted evaluation should not be an afterthought where we go back and say, oh, these models are not good, but it should be built into the data creation process. There's been a lot of work along these dimensions. For example, Samir Singh's group has been doing stuff say in checklists and stuff. And there's been work along detecting biases in models that could be seen along this lens. But the key point I'm trying to make here is that this sort of aspect-based testing should be part of the dataset creation process and not done post hoc. Let's see two examples of this, where I'm going to introduce two tasks and associated data sets, where the common theme is that in both cases, it seems like we can convince ourselves that our models are doing well, but when we evaluate a little more carefully, turns out they really are not. The first task involves understanding semi-structured data, tables, and the second one involves fact-checking. Let's go through this one at a time. We're really good at understanding tabular data. Just by putting phrases and numbers next to each other in a sort of a visually coherent way, like what you see on the slide, we somehow magically understand them. And the reason we do that is because we call upon prior knowledge, we use common sense. Essentially, we compose different kinds of inferences to make to be able to understand these tables. So what do I mean by that? Let's see an example. This table's been on the slide for a while, and maybe you'll be able to answer these questions. What can we say about these sentences? The first one is both men and women compete in the sport of dressage. We can see that the sentence is true because there's this row here called mixed gender, yes. And there's no lexical overlap or anything, but just looking at that, we can argue that the sentence is true. The second one is not true, and there are two ways of coming to that. FEI, the name, contains the word international, and the presence of the sport is worldwide, so the sentence is not true. So this suggests that we can set up a textual entailment or a natural language inference style problem, and that's what we did. We created this data set called INFOTABS to understand this task better, where premises, it's a natural language, it's a data set that's styled after natural language inference, where the premises are info boxes from Wikipedia and the hypotheses are natural language statements. And the task is to decide whether the hypothesis holds, is contradicted, or they are unrelated. We collected this data using Mechanical Turk, and this is, if we go back to what I said before, it's not enough to just collect training data, because the models that we train on this can fool us. So in other words, evaluating on a single test set is not enough, because these models have enough capacity to learn heuristics that mimic artifacts in the data. So we constructed multiple test sets of roughly similar sizes with controlled differences. The first one that we called alpha 1 is essentially distributionally similar to the training set. So it's a similar lexical makeup, similar domains as the training data. Alpha 2, we constructed it such that entails, we modified the hypotheses so that the entails become contradicts and the contradicts become entail, but these are like very tiny modifications in the hypotheses. The third one, alpha 3, contains tables from different domains. The fourth one, which we should have really called alpha 4, but it is what it is, contains data that is counterfactually modified. So for example, we created a pretend table about a pretend country called France, whose capital is Berlin. It doesn't exist in the real world, but we can modify the hypothesis also to be to reflect this change, to see whether models can actually reason about text, or they just remember what they saw in the pre-training. Well, the result is maybe not too surprising. Well, the surprising part is that a model that's built with Roberta was pretty good on the alpha 1 test set, which is the standard test set that we usually think of when we have a train test split. But by looking at the controlled variations, we were able to determine that this model overfits syntactic and lexical patterns. It remembers the pre-training a little too well. So it fails on counterfactually modified examples. Inoculating with a few challenge examples does not work. And really what we need is new ways to think about modeling and representations that can do this. Essentially, the model that we studied, even though it looks good on the in-domain or the alpha 1 test set, the model does not satisfy the implied contract that the definition of the task expects. Let's look at another example. This one involves fact-checking. Unlike tabular data, we are really not good at fact-checking, at least not instinctively, because we can't just look at a fact often. We end up getting fooled. We can't just look at a fact and say whether it's true or not, but with enough resources and time, we may be able to verify claims. Can we train statistical models to do this? There are efforts around the world to do that, to try. So can we do that? To study this question a little more carefully, we constructed a data set called XFact. It's a multilingual data set with claims, which covers, there are a couple of examples on the slide. There are about 30,000 statements that are labeled as being true of, as being factually correct or not. The data set covers 25 languages, and following the same philosophy that I just discussed, we have three test sets. Alpha 1 is, again, in distributionally similar to the training set. In this case, it's the same languages and the same news sources as the training set. In Alpha 2, we kept the same languages, but used different news sources. In Alpha 3, we basically changed the languages. So Alpha 3 involves unseen languages that were not in the training data. So we can now ask, how do models do on this data? So we built three kinds of models that look only at the claim, or look at claim and results from a search engine, or in addition, add some metadata about the claim. What we found is that all these models do okay on this test set called Alpha 1, which looks like the training set, but they are pretty bad, roughly as bad as chance on all the other two splits. In fact, with Alpha 1, with search snippets, the model performance is better than what a human annotator did, which is kind of disturbing. And the other sort of unsatisfying thing about this is augmenting with another 10,000 English claims does not help on Alpha 2 and Alpha 3. So once again, what this means is two things. First, the model does not satisfy the implied contract of the task. Namely, we are given some input, claim, and some associated information about it, and we need to verify whether it's true or not, and it should satisfy properties that go beyond what the training set has. And the other thing is that this is a modeling challenge. The other inference that we can draw from this is that this is a modeling challenge, and it's not clear how to address this problem yet. So let's step back up a bit. The big picture here is that it doesn't matter what the training data contains, but the fact that the predicates that are associated with the task specification should generalize to new kinds of examples, and I just talked about that. And it should satisfy certain properties that are specific to the task that we can write down without knowing anything about training, things like training examples. Let's look at two examples of this. I can, for the task of natural language inference, I can say if a premise entails the hypothesis and hypothesis entails another sentence Z, then the premise P entails Z. I don't need to know what the training data looks like. I don't need to know anything. From the definition of these predicates, of this predicate called entail, and just thinking about it, I expect this invariant to hold. And I can write down 4 other such transitivity properties. It turns out a fine-tuned BERT is inconsistent with the union of these 4 properties on a large percent of unlabeled examples. Another perhaps simpler predicate, simpler rule or invariant is from the definition of the notion of a contradiction. If a sentence P contradicts H, then H should contradict P. And it turns out BERT is inconsistent with this constraint on more than half of a large collection of unlabeled examples. We can build on top of this and generalize this. When we define tasks and the associated predicates, we can also, the domain experts can also declaratively specify what invariants they expect about these predicates. We can formalize these invariants as rules and measure inconsistency of models on some corpus. And the nice thing is, sometimes for these kinds of rules, we don't even need any unlabeled labeled data. We can measure inconsistency using unlabeled examples because the constraints might be, for example, implications. If certain condition holds, then some other condition should hold. It doesn't matter whether the condition really holds or not. The premise really, the left-hand side really holds or not in real data. So this gives us like a nice sort of a framework for evaluating models. So this is all I'm going to talk about, these contracts on predicates, where we can generalize to new kinds of examples, where I'm arguing that we should measure generalization to new kinds of examples, and we should measure the inconsistency with properties that we can declaratively specify. This might be a good point to pause for questions if there are any.
Yes, Vivek, I think there's a question in the chat. So how is I think this question is regarding the counterfactual examples. How is that different than the typical adversarial examples and training based on it?
Right. So this is a good question. It's different from adversarial in the following sense. Adversarial can take many different forms. Essentially, I want to tease apart what adversarial is. One kind of adversarial example is that the input that we are presented does not agree with what's out in the world. Another kind of adversarial could be, for instance, the text is ill-formed. The input is ill-formed. So there are different kinds of adversarial examples. Another kind of adversarial example could be where the input contains words that were not often used in the training data. Rather than just lumping them all into one category of adversarial examples, I'm essentially saying we need to group these adversarial examples as belonging to different types. That way, we will know exactly what kinds of adversarial examples break our models. I hope that clarifies things.
Thanks, Vivek. And actually, another question is just out of curiosity. So, when you deal with this, fact-checking task where you're using a table as a premise, in addition to, let's say, creating the counterfactual example by, for example, substituting the entities as a perturbation, have you also considered any structural perturbation, which means that, for example, we can change the rows or columns or orders or
so we did try that. In fact, the tackle paper has a bunch of experiments along exactly those lines. But the short version is there are certain kinds of perturbations that break the models. There are certain kinds of perturbations that do not. One thing that was curious is by simply permuting the table, the performance drops a little bit, but not too much. By deleting rows, and in fact, deleting a row that we manually determined to be important, we found that the performance did not drop at all, which is a little disturbing. So yeah, the paper has a whole bunch of experiments of that kind.
Oh, cool. That's very interesting. I would like to discuss with you during the meeting. And also, there's another question from Soumya. So, how to comprehensively decide the different aspects to probe in a model for some tasks?
Yeah, that's I don't have a good answer to that. My current best answer to that is you think hard about the problem and hope that we come up with an answer. But really, it involves thinking about not just the task, but also where the model is going to be used, what kinds of data is it going to encounter, and essentially what properties we require of it. I don't think there is, or at least I can't think of a easy way to come up with a global set of properties that is going to be task independent, because maybe this works for textual entailment, but what if I care about the task of, say, semantic role labeling, which is a very different flavor of a task. So at some level, this is where I'm pushing the work to to someone who's knowledgeable about both the task and where the models are going to be used.
Cool. Thanks, Vivek. Also, there's another question. How do these task contracts hold in comparison to contrast sets? So contrast sets, yeah.
Go ahead.
No, I'm just.
Yeah. So I think there is some connection to these things. I haven't thought too hard about this question, but I believe there is some connection. The one difference that I can think of off the top of my head is contrast sets are with respect to a model, I believe. So it's not with respect to the task definition, but with respect to the model. And if the model gets better, the contrast set becomes useless. So maybe I think there's room for both kinds of things. All right, I'm going to move ahead. In the interest of time, how are we on time? Oh, we are almost halfway through. Okay. I was hoping that I'll be a third of the way in by now. Let's see how far I get. So a natural question that comes up is, yeah, we can write down these sort of invariants about tasks. Can we use them to guide model behavior? Can we use them to train? And here, if you think about this question, really, this question is essentially saying we want to go from the paradigm of learning from examples to the paradigm of learning from knowledge. Knowledge can take the form of examples, but it can take the form of all sorts of other things. What do I mean by that? So essentially, the idea is that knowledge is more than just a tool to augment data, where data is defined as labeled examples, but knowledge is data. Good data sets are not easy to make. They take time, they cost money. It is, I think, somewhat easier to write rules about expected model behavior, contracts, essentially. These can be statements in first order logic. Sometimes, actually, at least most of the time that I can think about them, they are universally quantified statements that express invariants about the model. Some examples could be the example that we saw about transitivity, where entailment is should be transitive. It could be specialized knowledge about a task. For instance, for the task of semantic rule labeling, for any verb, certain argument labels cannot occur more than once. If you know the task of semantic role labeling, you'd see that this is part of the definition of the task. We could have other invariants that come from, say, if you're building, say, working on information extraction, we could say that people, let's say so we are working on the task of extracting information about persons, locations, and organizations and relationships between them. It's a trivial thing to say that if you have a relation called live in, a person should be the first argument of that. And the second argument of that should be a location. Otherwise, the relation can't be live in. Now, all of this is fine, but thinking about rules in first order logic and thinking about neural networks and trying to kind of fit them together puts us in this weird sort of a world where we are trying to merge neural networks with logic. Neural networks are easy to use, at least with today's infrastructure, and they're built with this idea of differentiable compute, where the fact that we have functions that can be whose derivatives we can take allows us to throw them into backpropagation. On the other hand, neural networks are kind of hard to supervise except with labeled examples. First order logic is not differentiable, as it's by definition discrete. As a result, it makes it hard to use with today's best infrastructure, namely things like PyTorch or TensorFlow. On the other hand, first order logic is expressive. It's easy to invoke for domain experts. What we want is the best of both worlds. To sort of merge these two universes, we need to address three specific challenges. We need to bridge the predicates in the rules with things inside neural networks. We need to make logic differentiable, and then we need to somehow use it. So let's go through this one at a time. The first one, namely, how do we find predicates inside neural networks? Actually, I've already answered this. All neural networks expose interfaces that have externally defined meaning. We've seen that labels can be seen as predicates, but the label is really the output neuron in a large neural network. You can argue that the output neuron is essentially expressing belief in this predicate called entail. Datasets can be seen as formal specifications. A collection of labeled examples can be seen as a large conjunction of these propositions. Collectively, we can, or generalizing this idea, I like to think of them as of this idea called named neurons. A named neuron is just this abstraction for nodes in a computation graph in a neural network that have some externally defined meaning. They could be output nodes like the entail node that we saw. They could be inputs to the network. And sometimes if we are careful about how we design our model, the internal nodes can also have externally defined behavior. One way or another, these named neurons are going to form the vocabulary for writing rules. So that answers the first question. The named neurons in a neural network are the ones that we will use to write rules about to write rules. The next question is, how do we make logic differentiable? There are multiple approaches that have been studied in recent years. The one that my collaborators and I have employed in many different tasks is to relax these Boolean operators using triangular norms or T-norms, which are essentially systematic relaxations of logic. There are infinitely many T-norms. Some of them are continuous and sub-differentiable, so they make them attractive. So let's kind of dive into this a little bit more. We have the 4 standard Boolean operators. Actually, we just need 3, but for technical reasons, we need the implies. In Boolean logic, both the inputs and outputs of these operators can either be true or false. They can either be 0 or 1. But specifically, let's focus on the conjunction to kind of illustrate this point. When both inputs to the conjunction are 1, the output is a 1. Otherwise, the output is a 0. I can think of the conjunction as a function that maps 2-dimensional inputs, 0 or 1, to an output that can be 0 or 1. So you can plot this like this picture. Now, I can relax this in many different ways by essentially putting a surface that agrees with the Boolean's conjunction at the 4 corner points and continues relaxes the middle region in different ways. And each such relaxation is a different T-norm. Here you see 3 different relaxations: the product, Lukasiewicz, and Gödel, and there are an infinite number of them. All 3 of these give us continuous and sub-differentiable relaxations. The important point here is, for all these relaxations, the inputs and outputs live in the range 0 to 1. You don't need to worry about all the expressions here, but the important point here is, when we want to use logic with a neural network, we can essentially use a T-norm relaxation. And that gives us, that takes care of the differentiability issue. In practice, we found that the product T-norm, a variant of the product T-norm called the R product, works best. But that's a technical detail. We can talk about that offline if you're interested. What can we do with this now? What can logic do for a neural network? Essentially, one way or another, what knowledge does for a learning system is it can introduce inductive bias. We can introduce inductive bias by changing the network architecture to networks that prefer satisfying the constraints. I'm not going to talk about this, but this is, if you're interested, once again, we can go offline, or I can point you, you can check out this paper. I'll spend a little bit of time talking about how we can introduce inductive bias by regularizing learning. Essentially, we will penalize models that violate the constraints. The starting point for this way of thinking involves the idea that knowledge and data are the same thing. Labeled data is a collection of propositions about examples. Knowledge is also essentially a collection of statements that may be universally quantified. Together, you can think of both of them as rules of this form here. Some L goes to R. I'm deliberately writing this in a very abstract way. For each particular task or an example, these L and R will take different forms. The goal of learning is to build models that are consistent with all of these statements. We prefer models that try to set all these rules to be true. Or equivalently, since we live in this relaxed, the universe of T-norm relaxations, our goal is to find models that maximize a T-norm relaxation. When we relax these the rules to these continuous and sub-differentiable functions, what we get are called inconsistency losses. I call it inconsistency loss rather than consistency gain, because we are going to be minimizing these functions. At this point, we can use any neural network to realize these predicates, any neural network library, and any optimizer, pick what you want. A cool sort of a side effect that we found was, if we use the product T-norm relaxation of the conjunction, and we do not have any knowledge except labeled examples, what we end up getting with this approach is the popular cross-entropy loss. Other relaxations give other losses. Do these rules help neural networks? I'm going to show just one quantitative example, and then I'll point to other instances of successes. We applied this on many tasks. With the task of natural language inference, we had two kinds of regularizers. Essentially, the inconsistency losses end up becoming regularizers from the two kinds of constraints that we saw before, the symmetry and the transitivity. And what we found is basically adding these sort of inconsistency regularizers improves the consistency of models. What is even more interesting is this kind of consistency. So the horizontal axis in both of these is different amounts of training data, and each plot here is for different inconsistency. So this one's for symmetry, this one's for transitivity. So in both cases, simply adding more labeled examples does not make the model more consistent. But adding the regularizer definitely helps. So logic-based regularizers help with consistency in this task. More generally, we tried this on, and actually other groups also have applied this idea for many different tasks: natural language inference, question answering, text chunking, semantic role labeling, doing things with digits, information extraction, and so on. And the general flavor of the results is across all of these is when we have very little data, knowledge gives better statistical models. We can inject these kinds of invariances into learned systems, which are surprisingly not learned even when we have a lot of training data. A bit of an advertisement. I encourage you to check out this Python library called Pylon that a bunch of us put together over the last couple of years that includes the ability to do these kinds of logic relaxation, but also has other ways of using logic in neural networks, including model counting and so on. So this might be another point where I can stop for maybe one question before I jump into something completely different.
Okay, so what about two questions? Because there's one question. So how do you see the relationship between this work and the field of neurosymbolic AI?
Okay, so the answer to that is I think this is part of neurosymbolic AI. Essentially, any work that tries to marry neural networks with symbols is neurosymbolic AI. This is one of the approaches that we can use to realize that broad idea. So yes, this is definitely in that.
Okay, so another question from myself. So there are different T norms there, right? Rukov-Zwick and product T norm. So can you give some instruction about how to decide which T norm to use?
Yeah, so this was actually the basis of this paper that's listed at the bottom of the screen. Let's see if I can get rid of that annoying PowerPoint thing. I have no idea how to, so I think you have to live with that. But there was an ICHKAI paper that we had where, oh, it's gone. So there was an ICHKAI paper that we had on evaluating different relaxations. And what we found was using a couple of different approaches, one that was slightly more theoretical, the one that was more empirical. The product relaxation, and in particular, a specific kind of a product relaxation that's called R product, is perhaps best suited both for its theoretical properties and also because it works well with gradient-based learning. The R product is essentially the product that's listed here. The implication, if you notice, is not the same as not A or B. It's something else. And if in the absence of any other information, I would say it's good to use R product, but actually in practice, there's a little bit more work that needs to happen because what we found was something that could be called a cousin of a vanishing gradient problem when we use massive formulas that are relaxed. So there's basically gradients don't basically exist. So there's a little bit of more work, that manual labor that needs to happen to make sure that we have good gradients, but without any other knowledge, I would say we should use the product relaxation.
Cool. Thanks, Vivek.
Thanks. Okay, in maybe the 10 minutes or something that's left, oh, we have 15 minutes. Okay, in the little time that's left, I'm going to talk about something very different. So far in the talk, I talked about using the language of logic to understand tasks understand models, and make models better. Now, I'm going to talk about a different approach that I've been playing with, which uses a geometric perspective that allows us to look inside models, inside representations, and make some decisions about which representations work well with which models. So the key question that we are trying to answer here is, labels carve up a representation space into regions. Can we examine how this happens by looking at the insides of BERT? The motivation here is, if we what we know from learning theory is, if we have the right representation, I say representation, think feature vectors. If we have the right features, all tasks are simple. If we have the wrong representation, whatever that means, then even the simplest task becomes complex. When we train classifiers with BERT, when we fine tune BERT and so on, the internal embeddings that BERT has get partitioned into, if you imagine a high dimensional space, the space gets partitioned into regions of different labels. Using this sort of a perspective, can we tell what makes one representation good for a task and not for another? The thing is, we can't just use classifier performance for this, because classifiers only give us a one-sided signal. If we have a good classifier on top of a representation, then we know that the representation is good because there exists a good classifier. But just because we were not able to find a good classifier, or worse, because we found a bad classifier, it does not mean that our representation is bad, because there are many other things that many other factors that are relevant here. Maybe we use the wrong seed or the wrong hyperparameters, or maybe we use the wrong kind of neural architecture, or we just didn't run the optimization to convergence. So to kind of get around this dependence, this issue, we started looking at the geometry of embeddings and classifiers. So using this cartoon example here, if you have some feature space, you have circles and triangles here that are placed on this feature space, every classifier, every separator between the circles and triangles can be seen as a surface or a hypersurface in a high dimensional space. When we try to find a good classifier to understand whether the embeddings, the feature representation is good, we essentially are picking one of many good classifiers, perhaps with inductive biases that come from learning theory. And the claim that a different way of thinking about it is, a representation is good if it allows us to successfully probe. Namely, if it supports more classifiers that are good and simple than another representation which does not support a lot of good classifiers. So this requires us to kind of think about features a little bit more. And so we defined this notion of an epsilon version space, which is a property of a feature representation, an embedding, if you will, and a data set. It's essentially the set of all classifiers that can achieve an error less than some epsilon on some data set using this representation. This is, of course, an implicit set, an infinite set. But if we can measure some properties of this epsilon version space, then we'll be able to understand the quality of this representation. What do I mean by this? Let's say that we have this data set here of circles and triangles, and we need to find whether the two-dimensional space on which that you see on the screen is a good feature representation for separating circles from triangles. We could train a classifier. But one thing we know for sure, without enumerating any model, is it doesn't matter what classifier we train, it has to cut through this shaded region. Every successful classifier should pass through this shaded region. So the idea that we started thinking about is, can we understand, try to characterize the properties of this shaded region directly without actually training a classifier? Every successful classifier passes through this shaded region, which means that every element of the epsilon version space passes through this region, because the epsilon version space contains successful classifiers and only them. So it turns out that characterizing this region is also non-trivial. So we built an approach for a piecewise linear approximation of this region by clustering points with the same labels. In the interest of time, I'm going to skip through the details, But what we have is essentially a heuristic that we call direct probe that kind of goes bottom up by merging points with the same label, by merging regions into convex hulls that are all have the same label. So you might be in a situation like this, and then you can merge things. At this point, we could try to maybe merge these two regions, and we can't because the combined region will intersect with a region belonging to a different label. So at this point, we stop. So this particular set of points gives us 4 clusters. And without knowing anything else, we can say, look, there are 2 labels here, 2 colors, triangles and circles, and there are 4 clusters. That means that this data cannot be linearly separable. That's an example of a property that we can identify. So just to kind of recap how we got here, our goal was to study a representation for a task. And we defined the set of interest, which is the set of all classifiers that give a low error on this task. We call this the epsilon version space. But it turns out this is an infinite set, so we can't do this. We can't build a set. So we then decided we want to look at the region between clusters of different labels, and it turns out characterizing that region is also non-trivial. So we built this heuristic that groups points so that the clusters groups points into distinct clusters that are all have the same label. Now, this is a bit that I'm kind of skimming over a lot of technical detail here, but essentially what this clustering process tells us is we can now use this, look at the clusters, and various properties of the clusters can tell us interesting things about representations and how they interact with various tasks. So we have experiments on many different NLP tasks here. And one obvious, maybe obvious, maybe not, but one immediate thing that we can say is if we can partition the data into these sort of clusters that are all have the same label, and if the number of clusters is the number of labels, then all we need is a linear classifier. A linear classifier will get perfect accuracy on the data. To our surprise, we found that the Roberta, before fine-tuning, did not satisfy this property for the task of part-of-speech tagging, which I still don't know why. Another thing that we can say is we have a conjecture. A larger epsilon version space, essentially a larger region between points of different labels, admits more good classifiers, and it can lead to better generalization. This conceptually might be related to the idea of margins and such things. Another way of measuring this, or a way to kind of realize this question, this conjecture, is we can measure the minimum distance between clusters of different labels. And this, if the distance is small, then we may not be able to accidentally find good classifiers. On the other hand, if this distance is large, if labels are really well separated, then we may be, the learner could accidentally stumble upon a good classifier. And so things like non-convexity might matter less. So it turns out by looking at distances between clusters of different labels, we were able to say that higher layers of BERT are typically better for most tasks. And this agrees with existing literature that use classifier probes. One thing that we could tell without actually training a classifier is just looking at the distances between the clusters, we could tell which labels might be more easily confused by any model that you're going to train on this representation, which I thought was pretty neat. We can use the same approach to examine the problem, the task of fine-tuning. Looking at the geometry of the clusters and the distances between them, we can see that fine-tuning, what it does is it's pushing the labels away from each other and also kind of simplifying the space by grouping different clusters belonging to the same label together. So essentially, both of these operations increases the minimum distance between clusters, and that could be seen as a sort of a geometric explanation for why fine-tuning works. In a fun experiment, we found that fine-tuning for one task and creates a representation that can help other tasks that are related, but can hurt some other tasks which are in some sense anti-correlated. This was a cool experiment to set up, and it was kind of expected, but it was nice to see that. We also found that higher layers change more during fine-tuning than lower layers. This was something that other papers have seen. And also, the embeddings essentially don't change too much after fine tuning. I know this is a lot of information that I just threw at you, but the short summary of this line of work is that we can peer into the embeddings and see how they sort of partition the space of labels. And the right set of tools for doing this could be from the areas of geometry or topology and such things. And direct probe is a heuristic for doing this. I encourage you to download and play with a Python implementation of this idea from this Git repository. But I'm going to start wrapping up. I think I have only a few minutes, so I'll start wrapping up. In this talk, I spoke about this idea of dissecting NLP models and putting them back together. And I took two different perspectives. You can take a declarative perspective that or the language of logic to understand and improve models, or you can take a geometric perspective to characterize representations without actually having to train classifiers. From the declarative point of view, by using this mental model of tasks as defining predicates and contracts, we can generalize how we evaluate models and maybe hopefully understand their behavior more, behavior and also their failures in a better way. Even more interestingly, we can use these kinds of contracts and invariants to guide model behavior, essentially train models to satisfy these invariants using this idea of inconsistency losses. Finally, I kind of gave you a little bit of a preview into this algorithm that we are calling, or heuristic really, that we are calling direct probe, which allows us to look into the models and see how they partition the space, the label space. All right, I'll stop now. I'll be happy to take questions about any of these things. And thanks so much for your attention.
Yeah, thanks, Vivek, for this very inspiring talk and also very great works. So any questions from the audience? Although we have already asked a lot of this.
Sure. And I see that we are almost at the end of time.
Yeah. Yeah, I guess just another question out of curiosity. So speaking about geometry, do you think that connects to, because recently people develop more complex geometric embeddings, for example, box embeddings?
Yes. So the question is, does this connect?
Yeah.
Yeah, so I think it does. I at a high level, I think it does. If you ask me how concretely it does, I don't know. I still am trying to kind of wrap my head around this. The work on box embeddings, and there's also these beta embeddings or something, allow us to essentially build, take this geometric perspective and compose regions into things. Where I get a little flustered with them is that these boxes in regions or that specify concepts are created or manipulated by passing them through neural networks again. So the interpretability aspect gets a little bit lost. So I don't know exactly how to reconcile this, but this is something that I'm trying to kind of put together in my head, and I don't know exactly how, but intuitively I feel like there must be some connection, but I don't know exactly what it is.
Cool. Yeah, I guess it's 12 already, so I already have a lot more questions, but I will save those during the one-on-one meeting with you. Yeah, but thanks.
Cool.
Once again for this.
Yeah, thanks so much. And if there are questions that come up later, shoot me an email. I'm happy to find other time outside.
Cool. Yes.
All right.
Okay.
Thank you so much.
See you soon.
Bye.